Hello, this is part of the Controlled Environment Plant Production Engineering / Technology Education modules that were developed and presented by The Ohio State University, Rutgers University, and the University of Arizona, with support from the USDA NIFA program. This module addresses supplemental lighting and shading and is presented to you by A.J. Both at Rutgers University and Pat McMahon at The Ohio State University. The learning objectives are: first, you should be able to understand the use and the design of supplemental lighting systems. Second, you should be able to identify the different types of lamps used for supplemental lighting systems. And lastly, you should be able to describe the different shading systems used to reduce the natural light intensity inside greenhouses. Additional references include several books and a website that I think will be very useful to review if you're concerned and have an interest in supplemental lighting systems. So I'd like to start off with briefly discussing what light is. Light is part of the electromagnetic spectrum, which ranges from cosmic rays all the way to broadcast rays, and only a very small portion of that is what we typically call light, and what we mean by light is typically the visible light, so the colors of the rainbow that we can observe with our eyes. Sunlight, however, includes more than just visible light. The spectrum coming from the sun includes also UV light and infrared light, or heat light, or heat energy. So the picture here shows you how visible light relates to all the other components of the electromagnetic spectrum, and it also shows you the solar radiation spectrum. And typically we identify different regions of the electromagnetic spectrum by the wavelength. When you think about light in terms of waves, we can associate a number to the wavelength, and then we can identify specific regions. So visible light starts at just below 400 nanometers and extends almost all the way out to 800 nanometers. The solar spectrum starts a little smaller, around 200 or so, or 250 nanometers, and extends all the way out to perhaps 3000 nanometers. The little image you see on the bottom left-hand side of your slide also identify what happens to light when it passes through the atmosphere. The yellow band, the yellow region, shows you the light that we could measure at the top of our atmosphere, so if you were floating in space. And then as light interacts with our atmosphere, primarily with gases such as CO2 and water vapor that absorb light to a certain extent, then you can see in the red region here what we end up at the surface in terms of the different wavelengths of light coming from the sun. So when we think about plant growth, we have to ask ourselves, well, what do plants need light for, or what do they do with light? Well, obviously plants need light for photosynthesis, the growth and development of plants. But there are other processes as well that are regulated by light. Plant can sense day length, or the length of the nighttime. We call that photoperiodism, and that is a signaling process that typically involves the start of flowering or the delay of flowering of plants. Photomorphogenesis is a process that affects the shape of plants as a result of light. When you think about germinating a plant in the dark versus germinating a plant in the light, you will notice that the plants grow differently depending on whether there's light or not, and we call that photomorphogenesis. Another process that is related to light is phototropism, where plants are able to direct themselves or direct their flowers towards the direction of the sunlight. And a good example of that is sunflowers that rotate their flowers during the day to face the sun, the path of the sun through the sky. And another process is called photodormancy, where seeds require a certain amount of light to start the process of germination. If you think about seeds being buried deep underground where it's very dark, they may want to delay germination because it would take a lot of energy to reach the surface. But if the seed is located closer to the surface where there's a little bit of light, that light then induces the process of germination and makes it easier for the plant to establish itself and to grow. So I want to close this slide with saying that we need plants to survive. Without the ability of plants to convert light into biomass, we would not be able to survive. So plants are really critical for our survival. There is, however, a difference between the sensitivity of our eyes compared to the plant's sensitivity to the light that we are receiving from the sun. And this particular graph is trying to show you these differences. So the eye sensitivity is shown by the red line and peaks at around 555 nanometers. The green line shows the sensitivity of plants, and you see there's a peak in the blue region of the visible spectrum, and there's a peak in the orange towards the red region of the spectrum. And so you have to keep in mind that plants respond differently to sunlight and to light from supplemental light sources than we do. In addition, there's another factor that is important to realize, and that is that researchers have identified the wave band between 400 and 700 nanometers as the photosynthetically active radiation band. In other words, based on the definition, plants use radiation within that band for photosynthesis. But if you look carefully at the line here that I show for plants, the green line, then you see that plants are still sensitive to light below 400 as well as above 700. So despite the fact that we use a definition of 400 to 700 to identify the photosynthetically active radiation, some processes in some plants are still occurring at other wavelengths. So keep that in mind. So why do we measure light? And how do we measure light when we talk about the light environment for growing plants? Well, first of all, the human eye, which is our light sensor, is not very good at determining differences in light intensity. And our human eye is perfectly happy functioning at very low light intensities that would not be sufficient for plants to produce enough or do enough photosynthesis to grow and develop properly. The other reasons for why we measure light is that it's good to keep a record, especially when you start comparing crops grown in different seasons or from year to year in different seasons. So we typically measure two things. We measure the intensity or the amount of light available for photosynthesis for plants, and in some cases we measure the spectral quality, and this is particularly important when you start thinking about different supplemental light sources and the different spectra or different light qualities they produce. We measure often at the top of the plant canopy just to get a good idea of what's happening, although we know that as you move deeper into the plant canopy, the light condition changes rapidly, and sometimes the spectrum changes as well. So we have to keep that in consideration, but the easiest way is to measure at the top of the plant canopy and making sure that the sensor is unobstructed by the leaves. And leaves can grow and change position as the crop matures. So you want to make sure that the sensor is always above the canopy. We want to measure frequently and preferably continuously, and luckily with the computer systems we have these days, we can hook up a sensor and that is easily achievable. So it's good to have that continuous record. If we do that regularly, we can also record the daily light sum, and research has shown that we can use the daily light sum to predict plant growth. And so that's a good number to know and to record to understand how much energy was available for photosynthesis, and as a result, how much the plants actually grew. I mentioned differences between wavebands. So the visible light has a slightly wider waveband than the photosynthetically active radiation waveband. And then the sunlight is even larger than that because sunlight also includes UV radiation as well as infrared radiation or heat radiation. So we use different sensors to measure these different types of light. We use foot candle meters and lux meters for visible light. We use quantum sensors for the photosynthetically active radiation. And we use pyranometers if we want to measure sunlight, including UV and infrared radiation. And then if we want to look at the spectrum and the spectral quality of light sources, we use a spectroradiometer that carefully can measure light intensities at different wavelengths. The units that we use are foot candles or lux for sensors that measure visible light, but I want to stress that using that for plant applications is not appropriate because the plants respond differently to light than our eyes. We use the micromole per meter square per second, or if we integrate that over a time interval, typically an entire day, we use the mole per meter square per second, per meter square per day as the unit. And if we measure sunlight, we typically measure the radiant component of sunlight, the radiant watts, and then we use the unit of watts per square meter. So this is not an electrical watt, but this is a radiant watt that we use. To show you differences in spectral output from various lamps we use as supplemental light sources for plant production, you can see here measurements taken by a spectroradiometer for an incandescent lamp, a metal halide lamp, a high pressure sodium lamp, and a blue as well as a red LED. And so you can see here by looking at the curves that these different light sources produce very different spectra of light, and so plants will have different responses to these different light sources. So when you think about adding supplemental lighting for crop production, it's important to understand these differences in spectral quality and spectral output for these different light sources. So when you think about adding light in greenhouses because the sunlight was not enough or the quality of the sunlight was not what you were looking for, and particularly now I'm talking about promoting photosynthesis, so promoting growth, we look at what we can add, what benefits we can provide for plants grown in greenhouses. So the first one is that we can improve crop production. We can improve by adding additional capability for photosynthesis. We typically can improve the plant quality, and we can also adjust the duration it takes to grow the plant to maturity. The next benefit that we are trying to accomplish is that we can improve crop timing. By adding supplemental lighting at key moments during the crop production cycle, we can make sure that the plant is growing at a predictable rate, and that means that we can predict when the plant is ready to be harvested. So supplemental lighting helps us improve the timing of the crop. But as we're adding supplemental lighting, we are typically also impacting the entire environmental control system. We are changing the environment. We are adding heat because the lamps are not 100% efficient in converting electricity into light. Some of the energy is transferred into heat. We're adding heat to the greenhouse. And that means that we have to worry about how this impacts our cooling system or our heating system. We have to worry about increased crop production, increased growth rates, and thus we need more water and we need more fertilizer. So the lighting system is a critical component, but as with many greenhouse systems, it interacts with other components of the greenhouse environment, and we need to understand these interactions to make sure we maintain the proper conditions throughout the crop cycle. Of course, when we add supplemental lighting, we increase the amount of money we need to run our facility. We need to buy lamps, we need to install them, we need to operate them, and obviously we increase the energy use or the energy consumption of the greenhouse overall. Supplemental lighting systems require a lot of energy. They are not that efficient, and the intensities required are relatively high. So we need a lot of energy to make this happen. Different light sources that we use as supplemental light sources. The incandescent lamp has been used primarily for photoperiod control, so to try to control the timing of flowering of certain crops. But as you know, incandescent lamps are slowly being phased out because they're so inefficient. Maybe only 5% of the energy going into an incandescent lamp is converted into useful light, and the rest is all converted into heat. So they're being phased out and replaced by, initially it was compact fluorescent, and now it's mostly LED light sources. Fluorescent lamps are mostly used in growth chambers and germination rooms. I'll show you an example of that. We use high intensity discharge lamps like high pressure sodium lamps or metal halide lamps. Those are, up until now, the most efficient light sources we have to produce light that is good enough for photosynthesis. However, the light emitting diodes are improving all the time, and the expectation is that in the near future, light emitting diodes will be the most efficient light source for supplemental lighting. However, this is a new technology, and with all new technologies we still have to discover benefits and drawbacks and applications. When you compare metal halide lamps to high pressure sodium lamps, then the metal halide lamp typically produces a little bit more blue light, which can be important for certain developmental aspects of plant production. But metal halide lamps also have a shorter lamp life and therefore need to be replaced more often, and that can of course add to the cost. And they're also a little bit less efficient, perhaps 25% versus 30% for the high pressure sodium lamp. So both lamps produce a fair amount of heat as they are operated, and that can be an issue when you're growing plants in greenhouses. So here's an example of a greenhouse equipped with incandescent bulbs, a simple string of incandescent lamps overhead, low light intensity to try to elicit this photoperiod response to try to either delay or start flowering at certain times of the year. Here you see LED lamps being used for the same purpose, for photoperiod lighting, for strawberry production, to try to make sure that the plants start flowering when needed and continue to flower for optimum berry production. An example of fluorescent lamps used in a growth chamber. Typically we use the tubes that, although not highly efficient, they provide a very uniform distribution pattern that is very handy for small areas such as in growth chambers and germination facilities. An example of a germination room equipped with LED lights on the right hand side. On the left hand side you see a traditional germination room with fluorescent lamps overhead. On the right hand side are the LEDs, and typically we use a combination of red and blue LEDs, because if you recall, I mentioned earlier that the blue color and the orange-red color are elicit the highest response in terms of photosynthesis in plants. So a combination of red and blue light is typically used, and hence the purple color that you see in this image resulting from that combination. An example of high pressure sodium lamps, in this case being used to grow roses in a greenhouse. I believe all these lamps are 600 watt and perhaps even 1000 watt. And if you count all the lamps in this greenhouse, you realize very quickly that this is a large energy consumer to try to provide sufficient lighting for photosynthesis in this crop. This picture shows you the comparison between the light produced by high pressure sodium lamps and metal halide lamps. The metal halide lamps are the more whiter color, and the high pressure sodium lamps are the more yellow color. And again, metal halide lamps are typically used because they provide a little bit more blue light, which can be good for certain developmental processes in plant production. An example of a research project that uses LED lighting installed vertically between plants as a trial to see if this particular layout would create benefits for growing, in this case a tomato crop, as opposed to a traditional system where you would have overhead lamps that have more difficulty getting their light to penetrate deep into the crop canopy. We also see mixed mode lighting systems, where in this case you see overhead high pressure sodium lamps installed in a traditional fashion at some distance above the top of the canopy, and you see bars of LED lamps installed in between the canopy. So in this case we're trying to again improve the light environment throughout the canopy to stimulate plant growth and development. But from a design point of view and from a measurement point of view, it becomes a lot more complicated to understand exactly what's happening within the plant canopy and how changes are occurring as you move through the plant canopy. When you think about designing supplemental lighting systems, you have to answer several design questions, and I listed some of the important ones in this slide. What are the operating costs? Obviously, this is something that is really critical for your greenhouse operation, so you need to know what the rates are, and you need to know what you can do by discussing with your power company in terms of getting special rates and special arrangements for using lights in your facility. Of course, you need to know what the crop requirements are. How much light does your crop require, and at what times of the day does it require that light? How many lamps are needed, because obviously that is going to determine the installation cost as well as the power consumption. Where can you put your lamps? So how much height do you have available between the lamp and the crop? And what kind of pattern do you install the lights in? I'm going to talk a little bit more about that later. How much heat is generated by the lights, because that obviously is going to impact your heating system and the overall environmental control in your greenhouse. You want to worry a little bit about light pollution, especially if your greenhouse is located in an area with residential buildings, because typically people don't like to live next door to a greenhouse that is brightly lit up at night. And then something that I think is very critical is you need to ask yourself, how important is light uniformity? And how do I define light uniformity? Is it spatial? Is it temporal? Is it within the canopy? All these questions are really critical and have an impact on the particular design that you want to install in your operation. One thing to remember is that light follows the inverse square law. That means that as you move twice the distance away from the light source, the light intensity is reduced by the inverse square of the distance, so by a factor of 4. And as you can see in this image, as you move further away, the overall light intensity drops rapidly. And so typically we try to install the lamps as closely as possible to reduce this effect, because ultimately you would end up with very little light on your canopy, because the light is spread out over a much larger area. The mounting pattern, as I mentioned, is very critical, and this slide shows you two different designs. One with even spacing, which is one you typically find in greenhouses where the electrician was told to hang certain number of lamps in certain rows. But if you go to a staggered mounting pattern, as I show you in the right-hand picture, you can see that you can improve the uniformity and perhaps also reduce the number of lamps that you may need over any given growing area. So the type of mounting pattern is really critical, and you need to put some thought into that to try to optimize your system. Here you see an example of a greenhouse with 2 rows of lamps installed at a fixed distance, and you can see on the far end wall that There's certainly a difference in the light intensity directly underneath the row of lamps compared to in between the row of lamps. And so this is an example of what I would call a non-uniform distribution pattern as a result of the placement of the lamps. You can make improvements by staggering the lamps between rows and within rows. And so this is done in this particular greenhouse, where the placement was carefully considered and optimized to make sure that there was a very uniform light distribution, in this case for a lettuce crop that stays a relatively short amount of time in the greenhouse and thus requires uniform conditions if you want to grow the plants at the same rate. So how many lamps are needed in greenhouses? This slide and this table is trying to show you approximations using 400 watt high pressure sodium lamps for a certain size greenhouse, in this case 24 by 180 long. And then depending on the light intensity that you're shooting for, in this case I used a micromole per meter square per second, and also for your reference the foot candle, although again I do not recommend using that unit for plant applications. You can then calculate how many lights you need given a certain mounting height and given a certain required intensity or desired intensity. So this table is trying to give you the number of lamps and the row spacing or the number of lamps per row that you need to try to get a fairly uniform light distribution based on the mounting height and the required intensity. We operate lamps, especially when you operate lamps with supplemental lighting, so for high intensity lighting, as much as possible during off-peak hours. Most power companies will have off-peak hours during the nighttime when the demand for electricity is lower, so the price is lower, and of course that has a major impact on your electric bill. The sensors that we use to sense and register the light intensity should be calibrated regularly and should be placed at representative locations. And we should, as much as possible, avoid shading those sensors because that means we don't get accurate readings. The control strategies that we use include a basic timer. We can turn the lights on and off based on the operation of a timer. We can also turn the lights on and off based on the light intensity. We can record the light intensity, and as soon as it hits a certain lower threshold, we turn the lights on, and as soon as it passes a certain upper threshold, we turn the lights off. Or we can look at, as I mentioned earlier, we can look at integral control, where we're trying to provide a certain amount of light throughout a daily cycle. So we track what light is provided by the sun, and then we start lighting at a certain point during the day to try to make up whatever the sun is not providing to meet our target. So there's different ways of controlling the lighting in greenhouses. We want to try to put in some time delays, especially when you use high intensity discharge lamps, to minimize cycling. LED lamps are much better in this regard. You can cycle them better, but high intensity discharge lamps cannot cycle very rapidly, so we want to put some time delays in to not have them turn on and off very rapidly. And some of these lights need some time to reignite. High intensity discharge lamps in particular, they will not reignite immediately after you've turned them off. They need to cool down before they can restart it again. When we do lighting, we also want to think about other environmental conditions, and one of the important ones is the carbon dioxide concentration. So if we do lighting, but we don't worry about the carbon dioxide concentration, we run the risk that the carbon dioxide concentration is too low. So we add supplemental lighting, which is expensive, but if the CO2 concentration is not sufficient, we do still not reach the desired plant growth and development. So we want to always make sure that we have enough carbon dioxide in the greenhouse when we run the supplemental lighting system. A confounding factor in all of this is that the lights are often operated when little ventilation is needed. So it's dark, it's cold, so we don't need a lot of ventilation. That means we don't bring a lot of fresh air in with added CO2. So it's really critical that you keep track of the CO2 concentration when you add supplemental lighting. So when we do CO2 enrichment, we go up to maybe as high as 3 times the ambient concentration, which currently is around 400 parts per million or micromoles per mole. Because if you go higher than that, it's typically not cost effective. So up to 3, sometimes 2 to 3 times the ambient concentration is sort of the maximum rate of CO2 enrichment we want to try to shoot for. In some cases, we can install cogeneration systems in greenhouses, and cogeneration systems burn a fuel source, generate electricity, and use the waste heat of the combustion process for heating the greenhouse. So we generate our own electricity. And when you think about the need of electricity for running a supplemental lighting system, these cogeneration systems can be very helpful. So if you have an opportunity to install a cogeneration system, then the technique of using supplemental lighting to increase plant growth and development could be an interesting benefit. In those cases where we do use cogeneration or combined heat and power, we could also try to capture the exhaust gases and clean them and use the CO2 in those exhaust gases as a supplemental source for the CO2 concentration inside the greenhouse. So in addition to generating electricity and heat for the greenhouse, we can also capture the CO2 in the exhaust gases and return them back to the greenhouse for improved plant growth and development. An added benefit of cogeneration is that you may be able to be less dependent upon the grid. If you have your own generator, some of your systems may be able to run on that cogeneration system when the grid is down, depending on your installation and safety precautions you've taken to isolate yourself from the grid. You may be able to sell electricity back to the local power company, which could be an extra source of income, an extra source of revenue. And you may be able to reduce the demand charges. Some power companies are looking at demand and usage by greenhouse operations and will charge very high rates for peak demand during certain times of the day or during certain seasons of the year. And so by having your own power generation system using a cogeneration system, you may be able to reduce or eliminate these demand charges. But one of the disadvantages or potential disadvantages of a cogeneration system is that you always generate electricity and heat at the same time. So in the summertime, when you don't need heat, you still generate heat, and so you have to have a process of getting rid of it if you don't need it, or at least try to make another use of it so you don't waste it, because you do generate both power and heat at the same time. Shading, of course, is needed when you think about supplemental lighting or light in general to reduce the amount of light. Particularly, we look at the heat load that is coming into the greenhouse and could generate heat stress for the plants. So when you think about light control, shading is certainly an important aspect of that. We have different techniques. We can use whitewash on the glazing. We can use screens. The screens can be inside or outside. They can be more permanent installed, or they can be movable, typically movable with a computer control system. And they can help control these curtains. If they're movable, they can really help control the daily light integral. You can really fine-tune the amount of light that the plant receives, both from supplemental lighting and sunlight, to make sure that you hit a certain target daily light integral that you are shooting for. And shade curtains, when installed properly, can sometimes have dual purposes, that in that they can also reduce energy loss and thus provide energy conservation in greenhouse operations. An example of whitewash on a greenhouse, a single layer, in this case sprayed onto the glazing of the greenhouse, reducing the sunlight coming in. The challenge with this system is that once you have it installed, it's not so easy to remove. So you typically install it for the entire growing season. An example of energy curtain installed in a greenhouse that can serve these multiple purposes. It can be used as an energy curtain at night and in the wintertime to reduce the heat loss. And during the daytime and in the summertime, it is used as a shade curtain that reduces the heat load coming into the greenhouse structure. We also have multiple curtains in some greenhouses. Here you see an example of a greenhouse where the energy curtain or the shade curtain has already been closed. But if you look carefully, there's also still a bunched up blackout curtain. So in this case, the grower has the opportunity to manipulate the day length by closing the blackout curtain, by reducing the natural day length. And of course, this is used to try to induce flowering or delay flowering depending on the type of crop you're growing. So multiple curtain systems are sometimes used for different purposes. Could be used for energy conservation, could be used for shading purposes, or it could be used for the manipulation of the day length. If you're considering supplemental lighting for a greenhouse operation, I think you have to worry about several different important issues. The first one is you want to make sure you understand the economics involved. So how much is it going to cost you not only to install and maintain, but also, of course, to operate. And so one of the suggestions we typically have for growers is, why don't you try it out on a small area to understand how it works and to understand the benefits that you may be able to get out of a system like this. You want to make sure you understand all the impacts on the crop, not only on photosynthesis, but also on the environmental parameters such as the temperature, the rate of water uptake, the nutrient requirements and things like that. You want to be able to choose an efficient luminaire. In efficient, I mean the conversion of electric energy into useful photosynthetic radiation. And so typically for that you need to consult with an expert who knows about luminaire design and luminaire operation. You want to check with your local utility company to make sure you get the best deal for the electricity that you need to operate your lighting system. If you do design lighting systems for greenhouse operations, it typically helps to use computer-generated designs, because you can manipulate different layouts, different lamp types, different placements more easily in those designs to really optimize the placement and the number of lamps that you need to provide a certain intensity. I suggest you always use a staggered mounting pattern, so you stagger the lamps between rows for optimized uniformity. You will always want to carefully evaluate the installation after it's been installed, so measure the light intensity carefully after the system is installed and go back to the supplier and ask questions if you think you're not getting what you've ordered. And last, but don't forget, maintenance. You need to make sure you replace lamp bulbs regularly when they burn out or when their light output is reduced to a level that is unacceptable. And perhaps you also want to have a system in place that regularly cleans the reflectors, for example, of some of those luminaires to make sure that they provide all the light and direct all the light to the crop that you need. When you think about LED technology, that is a new technology that is more or less just coming onto the market right now, I think you should be aware that we certainly haven't answered all the questions about this new technology yet. There's still a lot of research both on the technical aspects as well as on the plant growing aspects that has to be investigated and has to be reported on. So a lot of the systems that are currently in use are trial systems and are perhaps not economical yet. Uh, Obviously, LED systems allow for much more control over the light spectrum, so the quality of the light, and that has certain advantages. We can, for example, add more blue or add more red depending on which direction we want to steer the plant, and that is not so easy to do with other light sources. LEDs generate a lot less radiant heat, but they still generate convective heat, and that typically comes out of the top of the unit if you think about an overhead installation. So yes, they're not generating as much radiant heat, which could be helpful for trying to place them closer to the crop, but they still generate a fair amount of convective heat, and that heat has to be taken care of in the greenhouse environment in some fashion. The color output of LED systems, especially when you think about the combination of red and blue that results in a purple hue, can create some challenges for people that have to work in that environment. It's very difficult to distinguish different features in plant material when the plant material is lit with a purplish colored light source. It also may have some effect on people, especially when they step out of an environment like that and are exposed to normal lighting conditions. It may play a little trick on your brain, and you may have to adjust for a minute or two when you make these changes between these different light environments. I always suggest to try these lighting systems out on small areas first to get a better understanding on how they impact your crop and what the benefits might be. Deal with a reputable supplier is very important. There are many different lights available these days, and some are manufactured by suppliers that are more in it for a quick investment and a quick return, and not so much in long-term and reliable products. And I think it is important to investigate the warranty that these suppliers provide on their systems, and you should know whether the warranty includes the LEDs themselves or the entire system. And I recommend that you try to get a warranty on the entire system that includes the drivers as well as the other components that are needed to operate an LED lighting system. Finally, a few words about light pollution. Here in this picture you see a clear example of a greenhouse that is brightly lit at night, and you can imagine that if you were living close to this greenhouse and you wanted to go to sleep, you needed some heavy-duty curtains in your bedroom to try to block out all this light. And so depending on your location and depending on local regulations, you may need to reduce light pollution, and typically growers have to install additional screening inside the greenhouse to try to block as much of this light from escaping to the outside environment. Obviously, any light that escapes is not doing you any good, so it is in your own interest to try to reduce this light pollution as much as possible. We'd like to acknowledge the funding that was received for this effort by the USDA NIFA program.